just suppose we have a loop like this. The magnet forming like this, and the magnet is forming like this. So correcting loop is high. Get the option. Then the magnet is falling near the loop. Can you see the screen, right? So magnet is falling near the loop. This is a current capacitor. This is a conducting loop. So suppose the current in the loop is high. So we have to identify what will be high. It is zero, no current will flow, or current will flow clockwise or anti-clockwise, or it will change the direction. So both of these try this. Magnet is falling.
Sir, here I is the induced current.
Yes. Will there be any induced current? Not if it is. It is any idea how to proceed?
So option B.
So you are saying the current will be clockwise. Why it is clockwise?
No, sir. I mean, option C, sir.
Why it is anti-clockwise?
So since the magnet is approaching the loop will induce a current in such a way that the magnet will be opposed. So it will try to provide a north pole, and to create a north pole magnetic field, it must move in the anti-clockwise direction.
All right. Nifa, what's your answer?
Anti-clockwise, sir.
Yes. So both of you are correct. The current should be anti-clockwise, and we have Krishna needs also correct explanation. It should behave as a north pole. So yes, the current should be. Now see again. magnetic moving in question, what will be the direction? In question. Now,
So option C again.
D.
Yes, option C.
What's your answer, Anita? Yes, correct answer. C. Should behave as not polite. We'll try to attract the magnet because magnet is moving away. So again, it should behave as good or not simple. It should be moves in magnetism 3 4. And it is, suppose a magnet is just released. So what would be its acceleration? Well, acceleration will be greater than g equal to g or zero. Getting the question? Both of you?
So option A.
You're saying option A. Why option A?
So the loop will actually repel it, so the acceleration will decrease when it is falling.
Yes. Will again same type of thing. It will try to repel it. It will behave as not good. So obviously, because of repulsion, acceleration will not be equal to the issue. think we have to concentration. The 9 degrees diagram of here north south 20. Again we have to calculate.
So it will be option A.
So what's your answer, Anita? You see the diagram again and not tell me here. So if you relook the diagram, again check your answer why it should be. See, you see the diagram closely. This loop is actually broken. My point. So there will not be any induced current because of broken loop. Current is not, circuit is not complete. My point. Because of incomplete circuit, there will not be any current. So it will not behave as a north pole or south pole anything. So there will not be any opposition. Obviously, because of that, the solution is no opposition, so a solution is given. Getting my point?
Yes, sir.
Circuit must be completed. Circuit is not completed. In that case, someone asks you, so you can say current is zero, but EMF will still develop. EMF will be there, but current will be zero. Here, EMF induced will not be equal to zero. That will be there. One point will be plus and this should be minus for it. It should behave as south pole, right? But to repel it, it means current should be clockwise. It should be plus and this should be minus. So EMF will not be equal to zero. EMF will be there, but because of incomplete circuit, current will be equal to. Okay. Now coming to we have seen some questions from the last class. Question. Now go to to see this question. Question third. See this question third, both of you. This is NEET 2015 question. This one. So here the electron is moving as shown in the figure. Now the coil ABCD. So you have to determine the direction of current because of movement of the electron.
Sir, option D.
So saying option D. Why option B?
Not sure, sir.
Let's see. There is a loop like this. There is a loop like this. So what happens? Electron is moving from here to here to here. So because of movement of the electron, this electron is a negative charge. So current will be like this. there will be current associated with the flow of charge. So because of that, current will be in opposite direction. And we know that so it will behave as a current carrying wire. And we know that magnetic field due to current carrying wire is like this, mu naught I by 2 pi r, if we consider it. But we know that V is inversely proportional to R, right? So suppose the center is at a distance, we are considering the central point. So suppose this distance is R, right? Suppose this distance is R1, this distance is R2, this distance is. So when suppose we take 3 points like from B and C. So what will happen when the electron is at B? So this will we will treat the movement of electron as a current carrying wire. The magnetic field at B will be more than magnetic field at C, because B point is closer with the center. So when electron moving from B to C, obviously magnetic field is decreasing. The magnetic field is decreasing when the electron was moving from A to B, right? Magnetic field was increasing. When electron was moving from A to B, magnetic field was increasing. And when the electron was moving from B to C, magnetic field was decreasing. So when electron moving from A to B, magnetic field will decrease. Obviously, due to this leftward current, magnetic field will be in inward direction. So during the movement from A to B, inward magnetic field is increasing. During the movement from A to B, magnetic field is increasing in inward direction. So current will be induced such that it will oppose that. It means anti-clockwise current will induce so that it will be outward magnetic. Similarly, during the movement from B to C, magnetic field is decreasing in inward direction. So current will be induced such that it will increase magnetic field in inward direction, right? So obviously for that, current should be clockwise. Current should be clockwise because we have to increase magnetic field in inward direction. So direction of current will change during the movement from A to B and during the movement from B to C. Direction of induced current will change. It means what will be the most appropriate option? The current will be reverse its direction as the electron goes past the coil. It means most appropriate option is B. Understood? Both of you, any doubt, please ask. So simply you have to understand that when electron is approaching, magnetic field is increasing. So whatever be the direction of current, we are not bothered about direction of induced current. We just bother about like when the electron is approaching the coil, magnetic field is increasing. So current will induced in one direction. And when electron moves away, the current will be in opposite direction. Therefore, two directions of current will be there. Whatever it is clockwise or anti-clockwise. Here we are not concerned about the direction. That we are only concerned that the direction of current will be opposite, approaching and going away. Getting my point? Both of you understood?
Yes, sir.
Any doubt? Please ask. So this is how we should. You always remember whenever such kind of thing is there, electron is going pass away while direction of current will be in two directions. And whenever there is a continuous current, in that case, when we have a case like there is a current carrying coil near a circular disk. Suppose we have a situation like this, and there is a current carrying coil here. In that case, situation will be different. Here it will depend upon whenever current is increasing or decreasing. So in that case, if current is increasing here, so it can be like here if current is increasing. So what should be the direction of current here? Induced current. Suppose we have a current carrying wire near the circular wire and current is increasing in the wire. So in this case, what will be the direction of induced current in the coil?
So clockwise.
Correct. It should be clockwise because the current magnetic field is increasing in outward direction, right? Is basically increasing in outward direction. So we have to produce inward direction magnetic field, which means the current should be clockwise. So here only one direction of current is possible. Whenever it is increasing, it will be clockwise. Whenever it is decreasing, it will be anti-clockwise. There only one direction of current is possible in this case. But in the case of electron movement, there will be two directions of current. Some JEE questions based on Lenz's law.
So can you show the previous questions options?
Which one? This.
Yes, sir. Okay, sir. Thank you.
So let's do some JEE question. To question number one. This is JEE Main 2020 question. Try to solve this question. Both of you try this question number one. JEE Main 2020 question.
So option B.
Option B. What's your answer, Hanifa? So why option B?
So current will be produced if there is change in magnetic flux, and if the magnetic flux is constant, there would not be any change, right? So when it is completely inside the loop, that time there will be no current produced.
Yes, that is the explanation for second, right? Second.
Yes, sir. When it is at the end, like there is changing magnetic flux, so uh, the galvanometer will show deflection.
So if you see, deflection is also shown in option C and D also. Why not C and D?
So, but in C, it is shown that when the magnet is entering, that time the galvanometer has no change, so it's wrong, right? And when in D, uh, the galvanometer is entirely the opposite direction when it is completely inside.
So suppose I have a option like you are saying it is an opposite I of the option. So this is option. According to your explanation, it will also be correct, right? Should be correct, right? Suppose I am adding option E. An option, if you see option B there, both are same. Only the thing is that it is pointing down. So fortunately, your answer becomes correct. B is the correct answer option. But suppose in the question an option is given like this. So will it be correct? This should also be correct according to this direction. you're saying B is correct, right? B or C. You're saying B is correct. So your answer B is actually correct. But suppose I have in place of uh, D what is given in the question. Suppose in D this is given, right? Then how
Yes,
will
sir. When the magnet is entering, I think the current will flow in the clockwise direction, and the deflection will be shown on the left side, and it will be opposite for when it is exiting.
yes, that I wanted to. So at the entry point and at the exit point, deflection should also be in opposite direction. This is the third criteria. Second criteria is first criteria is the middle one should be straight upward. It should not show any deflection. And the deflection say first and third one should be in opposite direction. Getting my point? So these are two criteria. They might have made a mistake in making options so that if a student don't know the concept of opposite deflection, only by seeing the criteria of second situation, one can also give the correct answer, right? Only if someone's look only the deflection of second situation and he or she maybe see that like in A and B and C in option A, right? One is showing no deflection, so A should not be correct answer. And C is also not correct because one is showing no deflection. And in D, one is showing deflection, but in two it becomes opposite, so automatically the answer becomes. In the point, that is the advantage for this. They have not made proper option. But if someone don't understand the opposite deflections concept, that a student can also be correct. Getting my point?
Yes, sir.
So, all right. You understood, Hanifa? Our answer becomes B. Now moving to the next question. C option 70. Question 7. Question 7. this question. Can you see the question? Is it blurred? Kind of? Both of you go through this question. A magnet is slowly inserted inside a solenoid at a constant velocity. We have to find the appropriate graph for EMF induced. Both of
So
you understood the
option,
question? You're saying
so option D, I think.
D.
Yes, option D.
Why option D?
So current is produced due to change in magnetic flux at the end of the coil. So I think EMF also will be produced at that time.
The same thing, like current is induced. Basically, it is also it can be done by Faraday's law. So see, the same question is like previous question we have discussed in the deflection of the galvanometer. The same concept can be applied here. When the magnet will be completely inside, right? So in that case, flux almost will be constant and EMF will be zero. So during the uh, intermediate part, or when the magnet is well inside the solenoid, EMF induced will be zero. So obviously A and B cannot be the correct answer, since during the intermediate time they are showing maximum EMF, right? So it is not possible. So A and B is not correct. Now remaining options C and D. So we can predict that during the inward motion and during the outward motion, EMF must be in opposite directions, since in first case it is approaching the solenoid, and in the last case it is preceding the solenoid. So obviously EMF should be in opposite direction. So if you see options D, EMF is in same direction, right? Obviously D cannot be the answer. The correct answer should be C. EMF in both the cases should be in opposite direction. Getting my point? So this is the case. So correct option is C. Understood?
Yes, sir.
So this is how. Okay. So same concept is there. Same moving reflection. In both the cases, EMF should be in opposite direction. Moving to the next question. This was question 31. I think both of you have the same in the direction of current. All right. Now coming to very important the advanced 2020 question. If you go through this question, the advanced 2000. So both of you try this question.
So option B.
You're saying option B. Why option B? Why option B?
So there is no magnetic force produced which can change the direction of the motion. Or can stop the motion of the rotating light disk.
Then you're saying there, can you repeat?
So I'm saying that the magnetic, there will be no force which can like stop the disk from rotating, right? Not strong enough to stop the disk from rotating or move it in the same direction. So it will. No, sir, I'm not sure actually. So I'm just saying B.
Let us see. What will happen is that your answer is basically correct. But how it is, the option is actually B. Now the question is, why same direction? Why not in opposite direction? So suppose it is revolving like this in anti-clockwise direction. So what will happen because of movement of the magnet? There will be induced currents like eddy currents. Those are behaves as eddy currents on the surface. So because of movement of the magnet, there will be currents induced on the surface. Now, because of Lenz's law, these currents will try to oppose its motion. So eddy currents sometimes also acts as produces damping kind of forces. We know that eddy currents also can damp a motion or can damp a oscillation. So they will try to damp the motion. They will try to oppose the motion. So it will, if you understand terms of friction, so it will try to oppose its motion by damping force. If I am saying that damping force as a friction, so they will produce a frictional force or damping force on the magnet in the opposite direction of motion. Getting my point? Is true till now?
Yes, sir.
So suppose its motion is like anti-clockwise, so the frictional force will be in forward direction. But on the disk, what will the direction of frictional force? In the opposite direction or in the same direction of magnet. So obviously, force acting on the disk will be in the same direction of magnet. So the movement will also be in the same direction. Getting my point? So the disk will rotate in the same direction of magnet's motion.
So can you repeat it?
Let us see what will happen. You understood the why damping force will act due to the eddy current produced on the surfaces.
Yes, sir.
Not due to this eddy current, a damping force will act on the magnet. It means if we call the damping force as frictional force, the frictional force act on the magnet in the opposite direction of its motion. Getting my point? Suppose it is moving in this direction, so the damping force will act in this direction. The magnet. Understood it?
Yes, sir.
Now the same, but from Newton's third law, the force on the disc will be in opposite direction, right? There will also force on the disc from Newton's third law, which will be in opposite direction of this force, right?
Yes, sir.
And this force is opposed to the motion of the magnet. So this force on the disc will be in the same direction as that of motion of the magnet. Understood? It means the disc will move in the same direction as the magnet. Understood it now? Have you understood?
So which two forces you said will be in the same direction?
See, the disc is like this. Suppose the magnet is moving like this. So the frictional force on the magnet will be in opposite direction. Understood this?
Yes, sir.
So frictional force on the disc will be in this direction because of Newton's third law. If frictional
sir.
force on the magnet is in right direction, then frictional force on the disc should be left direction. Now you can see the direction of frictional force on the disc and the direction of motion of the magnet are in same direction.
Yes, sir.
Means disc will rotate the same direction as the movement of the magnet. Understood it?
Yes, sir. Yes, I got it.
So it's very simple. If you will go more into the deep, it will create you. So this is the simplest way to understand this. Understood, Hanifa? So this is how
Yes, sir.
generally the Edukiran concept is the lens law is basically a concept. This is applied in more of the questions. So direct questions are generally rarely direct questions are asked. That they advanced 2020 they have directly asked the question based. Generally we use this lens law to find the direction of current and how to mix with the Faraday's. So this is how we can solve questions based on this. All right, moving to the next concept. That is motional unit. Motional unit, that is the concept now. A difficult concept to understand. First, we will go through the concept and the questions based on emotional. So we already have the basic idea of motional unit. What is that? Whenever there is a rod or metal conductor moving through a magnetic field, what happens? It cuts magnetic flux. We say it cuts magnetic flux. Basically, we know that if rod is thin or something, how it will have any flux associated. But in such kind of motion, whenever there is a rod or a kind of rotating or like this or something is rotating in magnetic field. So what happens in such kind of motions, whenever there is a rod moving through a magnetic field, it cuts the magnetic flux. So due to this cutting of magnetic flux, EMF is induced across the rod. And that this phenomenon is known as motional EMF, the phenomenon of induction of EMF. Whenever a rod is moving like this end will be positive and this both of you understood why the upper end is positive and negative. This will be positive and this end will be. So basically you can understand it like motion of a charge. Whenever rod is moving, like you can understand it like a positive charge is moving like this. So what will be force on this positive charge due to the magnetic field? Magnetic field is in inward direction and velocity is in right direction. So if you do V cross V, the direction, we know that force on a charged particle. There are number of charged particles, there are number of electron charge carriers in the conducting rod. So what will happen? Electron will move like this. Electron will accumulate on this end and move and there will be deficiency of electron in this end. So this end will behave as positive end of the conductor. This end will behave as negative end of the conductor. Understood my point? So because
Yes,
of
sir.
that, an EMF is developed across the rod, and that is known as motional EMF, and its value we already know that is VB. And in other words, we can also say it like it's basically the actual formula for motional EMF is basically VBL we already know, but actual formula is like L. The actual formula is basically L dot E cross. This is the actual formula for the induced. This formula is valid. This formula is basically comes under the case whenever the movement of the rod is perpendicular to its length. It means when length, this formula is only applicable when length is perpendicular to the magnetic field and magnetic field is perpendicular to velocity. So both the three quantities V, B, L are mutual perpendicular. In that case, we can directly apply the formula VB. But in some cases, like whenever the conductor is moving at some angle, suppose the velocity is not perpendicular to the length, it is making angle theta with the length of the conductor. In that case, we have to take perpendicular component. We have to take V cos theta. And in that case, we will get EMF induced as VB L cos. Still here, angle between V and V is 90 degree, but angle between V and L is theta. So you have to take perpendicular of component of the velocity. Getting my point? So
Yes, sir.
this is the concept of motion and EMF associated with the conducting rod across a magnetic field. We also know that like whenever a conductor is rotating, like suppose we have a conductor like this. Is rotating this conductor is rotating with angular velocity omega and a magnetic field. In that case, suppose its length is L and magnetic field is inward or outward. So in that case, we know that EMF induced is half B omega L square, right? So for a rotating rod, the EMF induced is B omega L square upon 2. This formula, I think both of you know this formula, B omega L square by 2, whenever a rod is rotating in a line. This is also the concept of, based on the concept of motion. So this formula both of you know, B omega L square by 2.
Yes, sir.
Now coming to the next concept, you know, in the formula of E is equal to VBL, we must remember that the length basically we are taking is displacement length. What is this length? This length is basically displacement length. Displacement length. This is very important. So, like, suppose you have an arbitrary shaped rod like this, and if it is moving across a line, in that case, what will be the value of L? Value of L you have to take displacement, this length you have to take. Getting my point? Or suppose we have a rod of this shape is moving across a magnetic field. Suppose this was moving like this is also moving like this. So what will be L? L will be here, this diameter. Getting my point? So in the formula of VBL, L is basically displacement length, not total length. Understood my point?
Yes, sir.
That is the concept here. So based on that, let us do some questions of motional unit. So first you try question number 4.
So I'm not sure about the question.
A thin semicircular conductor ring PQR of radius R is falling, which is plane vertical in a horizontal magnetic field B, as shown in figure. The potential difference developed across the ring when its speed is V. So the same concept is there. A ring is a conductor of semicircular shape is running through the conductor, right? So as I told you, the EMF will be induced and we have to take the displacement length, right? We will apply the formula is equal to VBL, VBL. What will be L here? L will be PR, right? Displacement. What is PR? 2. So it should be 2R, right? So the correct answer is D. Let's prove my point.
Sir, and it's written like, and R is at higher potential. How so?
Same thing, like now what will happen, you can consider it as a rod of, you can consider the semicircular wire as a rod PR. You forget the semicircular wire, now you consider it as a straight rod PR moving through a magnetic. Its velocity. Now apply the same concept, V cross B, it should be positive and it should be negative. Understood?
Yes, sir.
So the R will be higher potential. Here you don't need to bother about higher potential because if you know the expression only, if you see in option D only, the expression is given at 2VR. Other are not correct. C is also not correct. D is also. But if you want to know the concept, this is the concept. Understood?
Yes, sir.
All right. Based on same concept, see question number 9. Also, JEE 2016 question. So do the question JEE advanced question. We'll go through this question in detail, write as a homework. Right. So I will give you some hint how to solve this question. Basically, what you have to do is it's it is moving with the rod is moving on a inclined plane with constant speed, right? This angle is theta. So if you consider the rod as the object, so what will happen? Its component of weight is mg sine theta along the incline, right? And
Yes,
the magnetic force will act in opposite direction, and that will be, we know that is ILB, right? We have to find the terminal speed of the copper rod is. So we have to find the terminal speed, the copper rod, right? So and what is the value of current? Current you can calculate I is E upon R. Getting my point? So if you
yes, sir.
equate this, if you equate mg sine theta, that should be equal to ILB, and I is E upon R. What is E? E is VBL upon, so I will be E VBL upon R and LB. So from here you will get V. What is the V? mg R upon BL square into sine. Getting my point? B square L square. So B square L square. So the correct option is, you see here, correct option is B, mgr sine theta upon B square. Getting my point? So the
Yes,
question
sir.
seems to be difficult, but it is very easy. What you have to do? It is given the rod is going with a constant speed. It means mg sine theta will balance ILB, and for the current I you have to put E by R, and EMF E will be VB. That is the point. Understood?
Yes, sir.